Thanks again for the invitation to be at the workshop. Today, I'll be talking about the subject of optimizing causal objective functions. Now, this is kind of a new expression or term. In fact, the problem that I'll be talking about today is relatively new, as you will see, and I will start by explaining what do we mean by this? What is the causal objective function and what does it mean to actually optimize it? Now, we know what an objective function is. You have some function f that provides scores to objects x, and the goal is to find those object x that maximize this particular score, right? This is very abstract, and depending on the function and its properties, there is all kind of algorithms for that. So we're solving an instance of this problem, except the functions that we're interested in are what we will call in this presentation a causal objective function. That's a new term, as I mentioned. And these are functions that score objects, which we will call units, based on how likely they are to exhibit a certain mode of causal behavior. So the new thing here is when I tell you what I'm interested in, or what is the score of an object, I have to really get deep into the theory of causality to even express this particular objective function. And we'll take, of course, a lot of concrete examples as we go on. The interest would be to do things like this. I want to go after patients who respond in a certain way to a medication. So the objects in this case are the patients, and these are the units. And the causal objective function would be a function that describes them. And I will find the right patients by optimizing that function. I may be interested in regions that have certain properties. The objects here, or the units, are the regions. Customers who are about to discontinue their service but would change their mind if offered a discount. Incentive policies that would keep customers engaged for the longest time. So these are all examples of objects or units. And then we'll see again that if we describe their properties that we want to optimize, we will end up writing functions that invoke aspects of causality. And let me say up front that even though the term causal objective function is new, we introduced this in a paper this year. I'll give you a citation to it later. This is actually inspired by a recent work by Lee and Pearl on the problem of unit selection using benefit functions. We'll talk about this in a little bit, but a benefit function is actually a special case of what we will be calling here a causal objective function. Now, to get started, we have to do a quick review of the basic elements we need to be able to express a causal objective function. And here we'll have to talk about the causal hierarchy. And later in the talk, I'll give you a pointer to online tutorials that elaborate even more. The causal hierarchy is a theory in causality that evolved over the last few decades and talks about three types of reasoning: associational, interventional, and counterfactual. In each one of these types of reasoning, we're computing probabilities of a certain type. The classical or prototypical question for association reasoning is something like this. We observe the random person of the population take a cancer medicine, and then we ask what's the probability they would survive. So this is how it looks. We're computing the probability of some event given some other event. It's a conditional probability. Classical has been studied forever. And the second is interventional reasoning, and the prototypical question is something like this. We ask a random person of the population to take cancer medicine, what's the probability they would survive? This looks almost the same as the first one, except in the first case, we observed passively someone taking the medication. In the second case, we actually intervened, like in a random trial, and asked someone to take the medication. The notation for this probability looks like this. In the first case, we use the conditioning bar. In the second case, we use the subscript. In both cases, we are trying to compute the probability of some event y. In the first case, we observed x passively. In the second case, we intervened to set the value of x. A huge difference between the two. You can think of the first as measuring the association between x and y, while the second one is measuring the causal effect of x and y. Think of the causal effect of x and y in this case as the therapeutic effect of the medicine on survival. In the first case, that probability will be measuring other things. So for example, if I observe someone taking medicine, I may conclude that they are likely in an advanced stage, or they are likely in a certain age bracket, because people who are in a certain stage are more likely to take the medicine and so on. So this probability is factoring more things than just the therapeutic effect or the causal effect of the medicine. In counterfactual reasoning, things get even more interesting. And a classical or prototypical question or probability is the following. A patient did not take the medicine and died. What's the probability they would have survived had they taken the medicine? There are two scenarios, a real one and a hypothetical one. The notation for this query looks like this. I observed this. This is the real scenario, did not take the medicine, and they did not survive. And now I'm asking, what is the probability they would survive had they taken the medicine? So these are basically the classical notations for these three types of reasoning. Counterfactual reasoning can actually get more involved than this. So let me give you another query. In this case, involves two scenarios, real hypotheticals. In general, it can involve an arbitrary number of scenarios. So for example, I may have the following question. A patient did not take a vaccine and died. And then what's the probability they would have survived had they taken vaccine 1, and would have died had they taken vaccine 2? And this query looks like this. So now we have three scenarios. Variable X has three values, X0, X1, X2. This means did not take any vaccine and died. And now I'm asking, they would survive if they taken vaccine 1, they would not survive if they took vaccine 2. So a real scenario and two hypothetical scenarios, and they're all in conflict with each other. We will actually end up using these kind of more involved counterfactual reasoning, just to let you know what's going to happen. So when we talk about causal objective functions, we will find that to express the causal objective function that we want to optimize, we will end up using quantities from all levels of the causal hierarchy. So these would end up being ingredients in expressing the causal objective function that we want to optimize. Now, people refer to this as the causal hierarchy, but actually there are two hierarchies embedded in it. The reasoning hierarchy, which we just talked about, and the idea is that as you go down, the reasoning becomes more sophisticated and closer to human reasoning, and this is the reasoning hierarchy. But there is also a parallel information hierarchy, in the sense that the information you need to answer this kind of query is not sufficient to answer the other ones. You need more information to answer this kind of query, and you need even more information to answer that kind of query. So these queries require the most information. If you look at it from a modeling point of view, you need a distribution to answer these kind of questions. And that's typically, in this theory, a Bayesian network. In this case, you need a special case of a Bayesian network called the causal Bayesian network, which has more information. In this case, you need something called the functional Bayesian network, which is a special case of a causal Bayesian network that has even more information. Functional Bayesian networks are what's called structural causal models. That's a more common name. So people would say, to answer counterfactual queries, we need structural causal models. And we will quickly go now and just talk directly about structural causal models. We need to look at them because we will use them to define the semantics of causal objective functions and how to optimize them algorithmically. So I will use this example from this paper. It's an excellent paper, which is long and give a very thorough treatment of the causal hierarchy. You can find it on the archive. We will use this to explain what the structural causal model is, but we will also use it later as a running example in a number of things we'll be doing. A structural causal model, which is, again, a functional Bayesian network, has a number of parts. The main part is what we call the causal graph, which is the DAG variables. Edges represent causal influences. So this means that X is causally influenced or directly causally influenced by these two variables, and so on. We make a distinction between two types of variables in these models or in these causal graphs. The roots, which are these guys, are called exogenous variables. And the non-roots, which in this case are X, Y, Z, are called endogenous variables. Now, there is a fundamental difference between them, in the sense that the only uncertainty here is that we have is over the exogenous variables. And we specify this uncertainty by giving distributions over these root variables. In this case, we're assuming that every variable is binary, has only two states, true and false. So I can specify a distribution over a root by a single number. And in fact, in this case, these are the distributions. So if you look at this variable, the small UR means that variable is true. If I put a bar over it, that means it's false. So all I need to tell you is that the probability of it being true is 25%, then 75% it's false, and so on. So these four numbers already give me the distributions over these variables, and that's the only uncertainty. Now, what do I mean by the only uncertainty? The assumption here is, in a structural causal model, is that for the endogenous variables, they are functionally determined by their parents. That is, once I know the state of the parent, I know exactly what the value of this variable is. So if I know the value of these two, that's already determined. There's no uncertainty, no probabilities. For this variable y, as once I know the value of this, and that, the value of this variable is completely determined. If you were doing a classical Bayesian network, you will use conditional probability tables. But in this case, it's more compact to use equations to specify these functional relationships. So in this case, I have three endogenous variables. So I have three equations. So if we look at the equation for x, this says that this is the function that determines the value of x, and it's in terms of z and this variable, and that's the equation. So this means z is true, this means z is false, this is an or, this means z is true and this guy is true, or z is false and that guy is false. Under either of these situations, x would be true, and so on. These are called structural equations. So that's a fully specified structural causal model. If you adjust for notation, it's just a Bayesian network, but a special type of a Bayesian network, and it's the one that we can use to answer any query in the causal hierarchy, whether associational, interventional, or counterfactual. Later, we'll talk about syntax and semantics. We'll see this more precisely. Now, here's the thing. So I need to say something important before we go back into what is a causal objective function and what does it mean to optimize it and so on. And this will also allow me to talk about the work of Lee and Pearl that motivated this work. If you have a structural causal model, as I said, then you can answer any query in the causal hierarchy at any level. In reality, though, you do not have a structural causal model, and you typically have only the causal graph plus data that could be observational or experimental or both. And that information is usually not enough to learn a unique structural causal model. So what do you do in this case? The work on causality has this genius idea that is practiced all the time. The information that you have may not be enough to specify a model, but let's not worry about that. Tell me what kind of query you're interested in. Because even though you may not be able to learn a model, you may be able to actually estimate the value of that particular query, but maybe not other query. So if the particular query you're interested in can be estimated uniquely from the given information, then the term people use is the query is identifiable. And a significant amount of work in causality and in this theory in particular is about identifiability. Under what conditions can I identify a query? And that, of course, depends on the type of causal graph you have, the kind of data you have, and the kind of query. Some may be identifiable, some may not be. And there is the work on identifying interventional queries and counterfactual queries. Counterfactual queries in particular are harder to identify, and people typically put bounds on them. It's very hard to estimate point values for counterfactual queries based on what is typically available in terms of information. So people put bounds on these things. Now, why am I stressing this point? I'm stressing this point because now we're going to go into the root of the problem that I'm going to be talking about, which is optimizing causal objective functions. So the problem, it was introduced a few years back, and that was called unit selection. This was the motivating example used in this work. The idea is I have a situation where I have customers that I may offer them a discount to encourage them to renew some kind of service. And these customers have some characteristics. And the question is, I want to know which kind of customers to target. So the customers here are the objects, are the units. And we're trying to select the units or the customers that I should target with this incentive policy. So what Lee and Pearl found, if you want to do this, you will end up writing counterfactual expressions in order to describe what you're after. You can think of 4 types of customers, what you might call a responder, someone who would renew if you offer them, but will not renew if you do not offer them. And to describe that kind of a customer, you're talking about how they respond to stimuli. You end up writing a counterfactual query that looks like this. If I intervene and make an offer, they will renew. If I do not make an offer, they will not renew. This is a counterfactual expression, and there are always takers, those that will always renew regardless of what I do, always deniers, that the guys that will never renew, it doesn't matter whether I offer them an incentive or not, and the contrarians, the ones that always do the opposite. If I offer them, they do not renew. If I do not offer them, they renew. So what you can see here is the connection between this notion of causality and describing objects, because the objects I'm interested in are ones that exhibit certain modes of behavior that needs causality to be described. In fact, in this work, Lee and Pearl went ahead and defined something that they call the benefit function. I'm trying to find customers to go after. So they use this expression, which says, what's the probability that this particular customer is a responder? What's the probability that they are a contrarian? These coefficients are things you choose, and that's basically an example of a causal objective function. And the goal here is to choose U that maximizes this expression. I'm after optimizing that expression. I'm after customers who will optimize this expression. But here's the interesting thing, and that goes to the relevance of this slide here, where I talk about the learning dimension. The focus of the work was on evaluating this. Now, if you want to optimize this, you want to be able to evaluate it. If you want to evaluate it and get point values for it, you need a structural causal model. But there is no structural causal model. There is only data. And the focus of the work was on trying to bound this particular causal objective function, going back to identifiability. And in fact, there was a sequence of papers that provided bounds and tightened the bounds. In fact, the work did not even treat the problem of optimizing that. The focus was back to identifiability. What can I say about the value of this causal objective function given the information that we have? Ang Lee is actually just graduated from UCLA. He did his thesis on the subject, and you can see that for details on this. So we took a different direction. Even though the focus here was the question of identifiability or how can I bound an expression like this, we found that there is actually a bigger story in a sense in what's going on here, which is a new computational problem that have not been treated in the literature. Later, when we go in the talk, you'll see that for associational queries, there are standard queries. We'll talk about 4 of them that have been studied for decades in terms of algorithms, complexity results, software systems. And now we'll see that we will define a new computational problem, which is optimizing causal objective functions or unit selection using causal objective function, which is an intriguing problem particularly from a practical point of view. And then we'll tell you what we've done about it in terms of algorithms and in terms of complexity results. So what we've done is we want to study unit selection from a computational perspective and under settings that allows us to do scalable things. So the first thing we will do, or we assumed, is that when we describe units, we will not use a single variable. We'll assume that you can have an arbitrary number of variables in the model that describe a unit. So remember, a unit here could be a person. So if you're talking about a person, you may want to talk about their age, their income, their education. So you need multiple variables for that. An object that you're trying to see that optimizes a particular objective function may be an activity. And then again, you may need multiple variables. So now there's an exponential space that we're searching over to select an element of. This is very important. So in this case, the unit is just a single variable. Bold, by the way, means a set of variables. So U is a single variable, bold U is a set of variables. So we have an exponential space. Now, But also, we're not dealing with the identifiability problem. We are assuming we have a fully specified structural causal model. Someone would say this is not practical. Well, we have to start there. In fact, all of the work on causality started initially by assuming that we have fully specified models. So this is a new work that's just starting, and we are focusing on the computational aspects. So we will assume that we have a fully specified structural causal model. And the other thing we're doing is we will be using a broad class of causal objective functions, of which the benefit function is a special case. The causal objective functions we will use, at least the ones we treated as far as algorithm and complexity results, have the following structure. It's still a linear combination of counterfactual queries, but these counterfactual queries are very expressive. They have 3 ingredients. Remember, this is the unit. This is or this is a set of variables that we're trying to optimize. So the whole point is to find a U that optimizes this expression. We allow evidence, which was not allowed in the benefit function. We allow 2 scenarios here. Each one of them is involving a different set of interventional variables, that is treatments, and 2 different sets of outcome variables. The benefit function, this was a single variable, the same. So this is pretty general. We assume that the units are roots in the structural causal model. Again, in general, you don't have to do this, but again, we have to start somewhere. So the problem we're treating now, I can define it formally, is the following. Assuming you have a structural causal model, and then a user comes and write a causal objective function in the following form, then the problem that we're treating is solve this optimization problem. Find me units. Find me instantiations of the variables, the unit variables. We call these the unit variables. Find me an instantiation of them that optimizes this particular quantity. Clear, well-defined problem. We will put it at the same level of other standard queries that have been treated for decades. Now, just to give you a sense of how expressive this particular class of objective functions, I'll show you some concrete example next. And by the way, this part of the talk is described in this paper that just appeared in the CLEAR conference recently. Using this class of objective functions, you can actually refer to structured units, as we mentioned, so you can have multiple variables to describe a unit, and optimizing the value of all of these. You can talk about compound actions. So you can have something like this. Which patients would have had COVID if they were to be vaccinated and exercised? So 2 actions, 2 different variables here that I'm doing simultaneously. This is the outcome, given that they did not exercise and were not vaccinated and got COVID. Again, I'm trying to optimize this guy. I'm trying to find a value for this that optimizes this quantity. You can talk also compound outcomes. These expressions get to be quite complex. So what you see here is intervention, another intervention, but I'm looking at the effect of this intervention on both of these variables. All right. So we'll in a second talk about this, the syntax and semantics of these expressions, because they get pretty involved. So that's the problem that we're interested in here. And I need to do 2 things before I tell you about how we solve this particular problem. The first one, I have to discuss the syntax and semantics of causal objective functions. So we treated them informally so far. So that will be a few slides. And then I need another bit of background on some algorithmic aspects of computing associational queries, because the approach we're going to be using is that when we solve this problem, this optimization problem, we will reduce it to an optimization problem of an associational query. So we will take our structural causal model and build a gigantic model, and then solve or optimize an associational probability on that gigantic model. That's the approach we're going to be using. So I need that piece of background on associational probabilities. So we'll do these 2 components, and then we will go to how we treat this problem. Now, syntax and semantic of causal objective functions. Let me just be clear that the form that we used here, we used it because it is general enough that allows us to do many things, but still specific enough that allows us to do something algorithmically and as far as complexity. But a causal objective function could be much more general than this. In principle, as you see in the paper discussion, any expression involving quantities from all levels of the causal hierarchy is in principle a legitimate causal objective function. And now we will explain the syntax and semantics of these things. So first of all, I need this important notation that people use on causality. If you have a structural causal model like this, and I want to do an intervention, like set the value of variable X to that particular value. So people talk about the notion of a submodel, which is another structural causal model that I obtain by doing two things. First, the variable I'm intervening on, I disconnect it from its parent. So I remove these two edges, and now it looks like this. And I adjust the structural equation for X, because here X was a function of these two guys. So its structural equation expressed its value in terms of these. Now X has a set value. So in addition to removing the edges going into X, I replace the structural equation for X, which in this example was this one, with this simple structural equation that says X has that particular value. This particular value is the intervention. And pay attention to the notation. If this is an SCM, this means the SCM I obtained by setting the variable X to this particular value. We're going to use it next. You will see next a few important notions about SCMs and causal reasoning. Some of this is standard, some of it is not standard. But in few slides, the outcome of this discussion will be, in the next few slides, you will see the general syntax of arbitrary counterfactual queries and how to compute their probabilities in a semantically very clear way. A central notion here is the notion of a world. In a structural causal model, a world is an instantiation of the exogenous variables. So if you look at this example, even though I have 7 variables, I have 4 roots and 3, a world or one state of the world is only described by the state of the exogenous variables, these guys. So there are 4 of them, they're all binary, so there are 16 worlds. Why? Because, as you know, and as we said, once you know the values of these variables, the values of the other variables, X, Y, Z, are completely determined using the structural equations. So if I'm talking about the joint distribution of that is specified by a structural causal model, I only need to look at the instantiations of the root variables. And again, in this case, here they are, and there are 16 of them. If you use the structural equation, you can infer the values of the other variables. This is a very important observation about structural causal models, which also allow you to compute the probabilities of each one of these worlds very easily. Why? Because the probability of a world is just the probability of this particular instantiation. And since these are all roots, the probability of this is simply a product of the probabilities of the individual variables. So computing the probabilities of each one of these is relatively easy. So if you look at this one here, I just need the probability that this is 0, false, 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 false. 4 numbers, I multiply them, I get this particular guy. Okay, I hope this is clear. Now that we know what the distribution specified by a structural causal model is, we will describe the notion of observational, interventional, counterfactual events, and then we will, in a couple of slides, be able to compute the probability of any of them very easily, because we want to be able to know what is a causal objective function syntactically, what does it mean, and what is its probability. So we talk about observational event. An observational event has the following form. You have some variables that are endogenous, and I have a value for them, and that is basically what an observational event is. It means that these variables, we observe them to take that value. These are examples of observational events. X is true. Another observational event is Y is false and Z is true. And here's another observational event, right? X is true, Y is false, and so on. An interventional event has the following form. X and Y are sets of variables, endogenous variables in this particular case. And this means that I set these variables to that particular value, and as a result, the values, the variables y took this particular value. So now I can have these kind of expressions. I set x to this value, and as a result, y took that value. I set x to false, z to false, and as a result, y became true. And here you see compound variables. So I set z to this and w to this. As a result, x took this value and y took that value. Clear. And now we can talk about counterfactual events, which is simply a conjunction of observational and interventional events. So this is a counterfactual event. What does that say? Currently, x is false, y is false, but if I set x to true, then y will be true. It's counterfactual because you can see the conflicts between these guys. These are not inconsistent with each other. I mean, this is possible that even though x is false and y is false, if I set x to true, y will be true. So this is meaningful event and we'll have a probability, and we'll see that next. This is a complex counterfactual expression. If I set x to true, y becomes true. If I set x to false, y becomes false. But currently z is false. And if I set y to true, then z becomes true. Complex things. And now you'll see very easily in a couple of slides how you can assign easily a probability to each one of these things. And therefore, you can talk about the probabilities of counterfactual events. So very good. We are missing only one slide, and then we take a concrete example of this. The secret slide, or the secret notion now is, now that we have the notion of a world, and now we have the notion of an event, we want to talk about when is a particular event true at a particular world. And remember what a world is. A world is an instantiation of these variables. So this is one world, this is another world, and so on. So the key notion we need is this. This notation is very important. This is not standard notation, by the way. This refers to a world, a particular instantiation of the exogenous variables. This refers to an event, like this one, for example. And we want to talk about whether this event is true in that particular world. And everything is with respect to a particular structure causal model. And for observational events, that's straightforward. If I want to know whether an observational event is true in a world, all I do is I look at the variable settings in that world and check if indeed the variables x are set to that value in that particular world. That's straightforward. The subtle one is what's coming next, which is an interventional event. So I have a world, and I'm asking, is it true that in that world, if I set x to these value, then y will take on that value? So I want to do this. I can reduce this to a question of the first type like this. Okay, it's very subtle. I take the model M and I replace it by this. This is the submodel that I showed you earlier how to compute, that you take the structural causal model and replace it by another one. And then I ask, in that model, is this true? So again, we'll see a concrete example next. And then for a counterfactual event like this, is it true in a particular world? Well, it's a conjunction. So if each one of the events is true and so on. All right. So let's see how powerful this is. Here's an example from this. These are the worlds, 16 of them. And now the question is, which worlds satisfy this particular event? Or here's the event. It is satisfied from these 16 worlds by these 4. Why? Because these are the only 4 worlds in which x is false and y is false. Straightforward. So if I want to compute the probability now of this event, I simply add up the probabilities of these worlds. Now, let's look at another example. Interventional event. This. Which worlds satisfy this event? That if I intervene and set x to true, then y will become true. I can do the exact same thing, but I want to do it with respect to this particular submodel, not the original model. Now, we can do this from scratch, but it's a good exercise to do this by modifying this example. this was the set of worlds for the original model. Now, what happened here? Here, X was following or computed based on the values of these two guys. But since I have set X to true, I'm going to just go and replace the values of X by true, because that's the value of it. It's a constant. It's no longer dependent on these. And also, since the value of X is this, I have to adjust the values of that. Because remember, what's the equation for Y? The equation for Y was this. But now that I'm setting the value of X to true, that equation simplifies to this, which means that simply the value of Y now is simply following the value of that variable. So those are the places where I have to adjust. So this is now the joint distribution for this guy. Now, we could have done it from scratch, but we just modified the joint distribution of the previous model. So now, if I want to know which worlds this event is true at, all I simply do is find which world make you Y true. And in this case, it's exactly these 8 worlds from 9 to 16. Those are the only ones in which Y is true, right? Here, Y is all false. So straightforward. And now here's what we have. The observational event, this guy is satisfied by these worlds. The interventional event is satisfied by these worlds. So now I can say that the counterfactual event, which is the conjunction of both of these, is satisfied by the intersection, by these 3 worlds. So now I can compute the probability of that counterfactual event by simply adding the probabilities of these 2 worlds. And so now I can, for example, compute the probability of this. What is the probability that Y would be true if I set X to true, given that X is false and Y is false? That becomes straightforward, and I get this number. So you can use this to basically define the meaning of any counterfactual expression or event and compute its probability. And by the way, this is the golden equation that says, how do you compute the probability of an arbitrary event that, as we saw, could be very complex? You just sum out the probabilities of those worlds that make it true, and everything rests on this notion of satisfaction, which we just defined. And as I told you, this is not standard. This is actually, you'll find these definitions in this paper that is on the archive. Now, you can generalize this a little bit more. You can do things like this now. You will not see these in the literature, by the way, and there is a reason for that. So look at this. Look at this expression, how powerful it is. What is the probability that a patient is a responder to medicine, given that they are not a contrarian? So this, look at this. Now, this is very meaningful, and you can, using what I just showed you, you can compute the probability of this thing. You can do something very complex like this. What is the probability that a patient would not have developed some symptom had they been on a diet, or alternatively have they exercised? So now we have disjunctions. The reason you don't see these expressions in the literature, because again, the focus is mostly on identifiability. Even the simplest ones that I showed you earlier are very difficult to identify or put bounds on. These would be significantly more difficult. We can afford to do this because now we're looking at the computational aspect of things. But I hope this shows you the power of this theory of causality as far as writing complex expressions that describe objects. Okay, just I need a couple of words on algorithmic aspects, and then we will talk about how do we actually solve this computational problem of optimizing causal objective functions, that is finding units that maximize their value. The algorithm we ended up using for this is the variable elimination algorithm. It's a famous algorithm. It's been around for decades. I don't know if people are familiar with it or not. We would not be able to talk about it here. That would take quite a bit of time. But I want to mention some properties of it, which are important, because the approach we're going to use is, you give me your structural causal model, you write your causal objective function, and you say optimize it. Find me those objects that maximize the value of this objective function. I'm going to take the structural causal model. I will build a gigantic model, which I'll explain to you how, and end up optimizing a classical associational probability on that. And I'm going to use variable elimination for that. The variable elimination algorithm is used on Bayesian networks. Here's, if you want a lecture or 2 lectures on variable elimination, my Bayesian network course on YouTube has that. Actually, this happens to be one of the most popular lectures in this course. We apply variable elimination to a classical Bayesian network. And remember, a structural causal model is a classical Bayesian network, except that the probabilities of the internal nodes are all zeros and ones. There are a number of associational queries that you can ask on a Bayesian network. These are the famous 4. This is computing marginals, and this is computing map. I'm going to go over these 2 in particular because the reduction that I'm going to show you will end up using these 2 queries. So if you have a Bayesian network like this, the marginal query is the bread and butter of association queries, which is this: compute the probability of some variable given some evidence. So in this example, by the way, this example is about a patient that can have a condition and 2 particular tests for detecting that condition and whether the 2 tests came out to be the same or not. So in this case, I'm telling you, the test 1 came positive, test 2 came positive. What's the probability that the person has the condition? So that's the marginal probability, all right? Or what's the probability that they're a male or a female? The other one that's more relevant to what we're going to be talking about is the maximum a posteriori hypothesis or map. This is an optimization problem. And in fact, when we do the reduction, we will reduce to map. What happens in this query is you're solving this problem. You have some evidence, and the user chooses some variables, and you want to find a value of those variables that optimizes this probability. In this example, the user said, look, I did the 2 tests, and the test came out to be the same. So the evidence is that the variable agree is yes. And these variables, the user chose them to be these 2. So whether the patient has a condition or not, whether the patient is a male or female, there are 4 possible values. And I want the one value that has the highest probability, which is this guy. So you can think of these as the unit variables, these 2 as the unit variables. And I want to find a value of these unit variables that has the highest probability given this. Now, that's not exactly what optimizing a causal objective function is, but close. So we will see that. One observation is optimizing this is the same as optimizing that, because you can write this like that, and we will get back to this later, all right? So whether you optimize this or that, it's basically the same. And in this case, this is the result of the optimization. That's the value of these variables that optimize this quantity. So if you want to think about it in terms of optimizing a causal objective function, it's very similar. I'm trying to find values of variables like I did here, but instead of optimizing this very simple association property, I'm going to be optimizing the value of this complex causal objective function. Also quickly, the main thing I want to say about variable elimination. So you can use variable elimination to do either this computation or the previous one. Roughly speaking, what variable elimination will do is it will eliminate variables from a model, something like Gaussian elimination. And in the process, it keeps eliminating variables until it finds the answer. The key thing about variable elimination is that the order in which it eliminates variables. So you can eliminate variables in any order. You will always get a correct answer. But which order you use affects the complexity of the algorithm. And you need what we call an elimination order to be able to run this algorithm. And each elimination order has a quality. It has a width, a number. This is defined using graph theoretic notions. We're not going to do it here. But if you use, one order, it may have width 3. Another order, it has width 5. And the best order that you can ever get, its quality is called the Treewidth of the DAG. And intuitively, this is tied to how topologically connected the structure of the Bayesian network is. So in this case, as you go this way, you expect the Treewidth to become higher, right? The key thing about variable elimination is that it can compute this query marginals in this complexity. So linear in the number of variables in the model and exponential only in the width of the used order. So if you're able to get orders that have small width, then this is very efficient. Otherwise, the algorithm is not efficient. The other main thing I want to say about variable elimination is you can also use it to compute map, not just marginal map. But the difference is you can no longer use any elimination order in this case. The elimination order that you must use to compute map has to be constrained, meaning the map variables, the variables you're optimizing, has to appear at the end of the order. That means you do not have all total orders at your disposal. You only have a subset of them. And that subset, the width of those may be worse than the others. That's why map is more difficult than, in general, computing map is more difficult than computing marginals using variable elimination, because you cannot use any elimination order. In the first case, any elimination order will work, so you can use the best. But that best elimination order may not have this property. It may not have the map variables at the end, so you may not be able to use it, and you may have to use a worse guy. I hope this is clear. I have some couple of very nice slides to talk about complexity classes, but we're going to skip this. I have a way to describe complexity classes using boxes and paint. We're going to skip this. The main thing is to know that map has this complexity class, which is something we're going to be referring to later. Okay, so we have the ingredients now to talk about how do we optimize causal objective functions. Here's the key insight. The key insight is that a causal objective function on a structural causal model can be reduced to a classical associational probability, but on an extended model that we're going to call the objective model. So we're going to take the structural causal model and build a large model that we're going to call the objective model, and use that to solve the optimization problem. And this reduction, which I will sketch for you next, allows us to first characterize the complexity of unit selection. It allows us to develop the first algorithm for solving this problem exactly using the broad class of causal objective functions that I've mentioned, and to allow us to give bounds and so on. Remember, that is what we're trying to optimize, a causal objective function of the following form. That's the problem we're trying to solve. Now, the first thing you have to realize is this has n components. So we're going to refer to each one of these as a component of the causal objective function. And we're going to do the reduction in two stages. First, I'm going to show you how you can take this component, which is a counterfactual query, and reduce it to the computation of an associational query. Now, that part is relatively standard. And then the second part is how to do the linear combination, how to compute the linear combination of these counterfactual probabilities, again using an associational probability. That's actually new. That's one of the contributions we had recently. So how do we do one component? As I said, this is standard. So let's say you have this, and you have this particular counterfactual query. What we have here is some observation and two scenarios. We discussed this in detail yesterday at the tutorial. Later, I'll give you, again, pointer to the causality tutorial where you talk about this. But the point is, you construct what we call parallel models. So think of this as talking about one world. In this case, I need to talk about three different worlds. The world in which X and Y are true, another world in which if I set X to false, then Y becomes false, and a third world in which if I set X to true, I get Y is true. So I need what we call a triplet model. In the tutorial yesterday, we only talked about twin models because we were looking at simpler counterfactual queries. This is more involved. What you're seeing here is this guy replicated 3 times, except that the root variables are shared between the 3 copies. This may not be obvious from the topology, but that's exactly what's going on. Just 3 copies of this model where the variables U and A are shared between the 3 copies. The notation is this is one world, single brackets is another world, and this is the third world, right? It's not a great notation. It's going to get even more complex in just a little bit. And now that you have this, you can actually emulate interventions by computing a submodel of this. And as we discussed earlier, So you get a mutilated triplet model like this. And the point is, this counterfactual probability is the same as this associational probability. Look what happened here. Conditioning bar. This observation here is on this world. This intervention is on this world. This intervention is on this world. And now I'm computing the probability of these two outcomes. This outcome is on this world, and this outcome is on that world. But the point is, this is now an associational probability. So now we are in the world of associational probabilities, which is good because we can fall back on classical algorithms like variable elimination. Okay, so again, this is standard. This is, is known. Now, how do we do all components? Because our goal is to compute this, not that. I showed you how to do this. And the way we do it is, you have to construct for each component one triplet model. So if you have like 5 components in your linear combination, then you have 5 triplet models. And then you combine them by making sure that the unit variables, the variables you want to optimize, are shared between all triplet models. That's not enough. You have to add this additional variable h as a parent of all outcome variables. And that is the one that we need to represent the linear combination of these things. We call this the mixture node because it allows us to compute a mixture of n probabilities. Here's how it looks pictorially. And to simplify it, otherwise the graph will look very complex, I'm using this kind of an objective function, which actually does not require a triplet model. It requires a twin model, but it's the same. So I have 2 ingredients. So I need 2 twin models. I need this to compute this guy, like I showed you earlier, and I need this to compute this guy. And the u variable that I'm trying to optimize is shared between them. And now I added this mixture variable. Now, this construction would require that you adjust the equations of these things. You can do this in a systematic way, and that's done in this paper here. But the main point is, this objective function, causal objective function, its value on this SCM is exactly this associational probability on this gigantic model called the objective model. This is large. If you have 10 components, you're going to have 10 of these guys. But even though this looks like a nasty expression, it has a very specific structure. It has an observational event given an observational event, comma, the unit variables. So more generally, what we were able to do is to solve this optimization problem. That is, to find the units that optimize the value of this causal objective function. You can solve this problem by finding the units that optimizes this associational probability, but on the objective model. Now, what is this? This is not something that has been studied. The closest thing to it is map. Remember our friend map? Map is this. The difference is, in map, what I'm optimizing is before the bar. And here it's after the bar. And that ends up having implications, but it's close enough, right? We ended up calling this problem reverse map. It's not something that if you open a book in on probabilistic graphical models or Bayesian networks, you'll find this discussed or algorithms for it. You will find this discussed and algorithm for it, but not this. So what we did is reduce the optimization of causal objective functions to the optimization of reverse map, which is an associational quantity. The key thing is we showed that this is also NP to the PP complete, the same complexity class as map. So even though it looks different, it's equally difficult for these particular objective functions because we're working with a specific class. And interestingly enough, we said that the unit variables we're trying to optimize are roots. Now, they can be a subset of the roots, but if they are all roots, then the problem becomes NP complete, so it becomes easier. So if you're optimizing over all roots, That's easier than doing a subset of the roots. How do we solve this problem? And here I'm just going to give you the sketch of how this works. We don't have an algorithm for this. We have an algorithm for map using variable elimination. And now we need an algorithm for this. And we're going to use a variable elimination for that as well. The trick is this. If you look at how variable elimination is used to solve map, it looks roughly like this. So suppose your model variables are these. These are the ones you're optimizing, and this is the rest of the variables. So in map, you are trying to solve this optimization problem, which, as we said, is equal to that. And this is the same as this, right? I'm just marginalizing over all other variables in the model. So what map will do is variable elimination will say, okay, I am going to eliminate these variables first, and then I'm going to eliminate these variables last. And then I give you the answer. And as we discussed, the complexity of this algorithm is this. N is the number of variables in the model, and W is the width of the elimination order, which must be constrained. It must be an elimination order in which these variables, the map variables, are last. Now, I can't use this. Why? Because the one I want to solve the optimization problem is this. This one is, you unfold this, you get the following. Now, if I want to optimize this alone, I can use this algorithm. If I want to optimize this, I can use this algorithm. But I can't do it here because, like, you know, first, this doesn't fit that, and you can't do something like this. Like, you can say, maximize this using variable elimination, minimize this using variable elimination. That's not going to work because the two U's have to match, right? So what we did is we found a way to rewrite this expression in a factored form that allowed us to run two versions of variable elimination in parallel so that they are synced. So they are optimizing this expression in a sense while maintaining the same U. Of course, we don't have time to go over the details. The pseudocode is straightforward in the sense that if you look at the pseudocode for the classical variable elimination algorithm, it's very similar. In fact, it has the same complexity. So if you are able to use an elimination order with a certain width to solve this problem with this complexity, we can use that same elimination order to solve this variant, except that we'll be running two parallel versions that are coordinated in some subtle way. I'm not going to go over the details here. We don't have time for this. But check the pseudocode, and there's a concrete example in the paper in addition to the pseudocode that traced this by hand of how this version of variable elimination run on a Bayesian network to solve the reverse map problem as opposed to the map problem, right? And again, to see the big picture once more before we move on, what's going to happen is this. You have this. You want to optimize this guy by finding the value of U that maximize this. You end up solving reverse map on this guy. So you find U that optimizes this. And you do that by running this reverse map variable elimination algorithm on this model. All right. So I want to end with a word on empirical results and tell you about two other main developments that also are underlying this work. If you want to compare this algorithm that I just told you, if you want to do experimental results, so you have the baseline. What is the baseline? The baseline is the following: brute force, right? So you say you want to optimize this. How many unit variables you have? I have 20 unit variables or 30 unit variables. Okay, let's say 20, more realistic. They're binary. So 2 to the 20, right? You look at every possible instantiation. That's a large number. And for each one, you evaluate this guy, and then you pick the guy that has the highest probability. Okay. Now you think it's this algorithm is exponential in the number of unit variables. No, it's worse. Why? Because if I give you a particular instantiation of the unit variables, you have to evaluate this. And to evaluate this, you have to evaluate each component. So to evaluate each component, you have to run inference on a triplet model. So you have to run variable elimination to compute marginals on this. So the complexity is exponential in the unit variables multiplied by the complexity of variable elimination on a triplet model. All right? Because you need to do that to evaluate the project function. So this is what this slide here is trying to say. The baseline, you enumerate every possible instantiation, that's exponential in the number of unit variables. But then to evaluate this, you have to have this complexity. This is the number of variables in the triplet model. And what is W? W is this plus that. This is the width of an elimination order that you need on the triplet model, right? So you have to add this with that, and that's the complexity, as opposed to running variable elimination on the objective model. N1 here is the number of nodes in the objective model, and W1 is the width of an elimination order on the objective model. So really, if you want to compute the brute force with this, it comes down to computing this number with this number. Here you're exponential in this, and in the base, you're exponential in that. Now I have to take, excuse me, this algorithm, variable elimination, is the simplest thing that you can ever construct. And we started with it because this is such a new problem, and it's already quite complex to even get to the point where we started the algorithm of this work. So you'll see in the paper quite a bit of experimental results, quite extensive. There's actually a long appendix, but just to give you an idea of the exponent, the bottom line, of course, is this is more efficient than the brute force, and the improvement increases as the problem gets larger. That is, as the number of SCM variables increase and as the number of unit variable increase. But just to give you an idea of the difference between the exponents. So the brute force, the exponent will be this, the algorithm will be that. The brute force, the exponent will be this, that. The brute force, the exponent will be this, and in this algorithm, it will be this particular one, and so on. There is quite an extensive analysis of what's going on here. And I'll just point to one thing before I try to wrap up with a couple of important observations. One of the questions we look at, is reverse map always tractable on the objective model if map is tractable on the underlying SCM? So if you're able to efficiently solve map on the SCM, does that guarantee that you will be able to solve a reverse map efficiently, but on this gigantic model, which is the objective model? And the answer is yes. And the way we show this result is we show that if you have an elimination order that you're using to solve map on the SCM, we can automatically construct an elimination order for this large gigantic model that is only within a constant factor in terms of width. So there's quite a bit of algorithmic and complexity results in the paper. Okay, let me conclude by saying a couple of things. The complexity results that we obtained for this paper are based on some fundamental results that appeared in another paper that will be presented this summer in Ichikai. This is about if you have an elimination order for a causal graph, and now you're working with a twin network or a triplet network or a quadruple network, and you have an elimination order for this of a certain width, can you automatically construct an elimination order for this while guaranteeing me that the quality will not blow up. And there's the fundamental theorem is this. If you have an elimination order of for this graph, and it has a certain width W, then for a twin network, I can construct automatically an elimination order whose width is this. So basically, I can just double the width. More generally, if you have what we call n-world network, so this is a 2-world network, this is a 3-world network. Depending on how complex the counterfactual query, you may need 5 worlds. We have this theorem that basically bounds the elimination order quality of these parallel worlds. Before this work, people will construct elimination orders using heuristics. Now, if you use that heuristic on this, it will work. Now, if you want to work with 3 worlds, you just run the heuristic on this because this is just another graph. And in this work, we said, no, this is not just any graph. This is a graph that's obtained from this in a very particular way. So we can do better than simply running the algorithm on this. We can run the algorithm on the smaller graph. And when we get the elimination order, we can automatically construct something for this and still guarantee you something about its quality. So this is studied in detail in this paper, which you can also find on the archive. I'm going to skip this. There is a slide on a new notion called causal treewidth. Let me leave it for discussion. This is a new major development. We have not used it in this work yet, but it appears in this paper. Let me just say it in one word, and if someone asks about it in the discussion, I will get back to it. For structural causal models, because they have a specific property, there is a more refined notion of treewidth called causal treewidth that can be significantly smaller and can have dramatic impact on improving the quality of the algorithms. And I can explain it in a couple of minutes, but let me just do that in the discussion and get to the concluding slide. Main messages. There is a new computational problem on the table now. If you look at associational queries, people will tell you there is computing marginals, there is computing MPE, there is computing map. Classical computational problems have been studied for decades. If you open up any of the books on Bayesian networks or graphical models, you'll find chapters dedicated to these algorithms. What are they? How can you use them? Various algorithms for doing them, exactly, approximately complex results. This unit selection in this fashion, using this new notion of a causal objective function, is a new entry. Work of Lee and Pearl is the original idea. We set it up here in a general way and treated it as a computational problem as opposed to an identifiability and learning problem. As with other work on causality, you start with the idealized case, and then there is the practical case. Here we're starting on this, and our intention is, of course, to go to the more practical setting. But that's also the chronology that people followed. Sometimes people tell you, but you're assuming a fully specified model. That's not practical. Well, yes, that's how things started before people started having all of these nice results about identifiability. People started by first computing counterfactual queries using twin networks, and there was the major discovery. And then people started trying to identify and estimate these. And we think this is a natural chronology. The other main message is there's some really exciting new algorithmic developments that are dedicated to problems and causality. One of them is what I just showed you, this notion of the treewidth of parallel worlds. And the other is this notion of causal treewidth, which I skipped that slide, but I'm happy to talk about. So with that, I'd like to finish. Thank you. And I'll be happy to answer any questions that you may have.